All right, so I'm going to talk, so today's lecture is sort of going to continue the introductory component of the school. And so this is going to be yet another opportunity for us to think about non-linear dynamics. And if I were to maybe sum up what we were like broadly what we were talking about in day one, especially the first half of day one with Daniel's lectures and Abby's lecture, maybe what we were looking at a lot is species, like single species dynamics, right? So what happens if you just have one species or a population of one species? How would it grow? Maybe how would it saturate, and so on and so forth, right? And then sort of all of this, you know, especially when we were talking about logistic growth, we were making some assumptions for maybe why this population should start saturating, right? So can someone say why we would expect this population to saturate at all? Like, why should exponential growth not go on forever? Yes. Finite resources, right? So, okay, so there's some notion that we already have in the back of our head that there are some resources out there and populations grow because they're consuming these resources. But okay, I mean, these resources are around, but they're not going to be there's not an infinite amount of them. So eventually, you're not going to have enough resources to be able to sustain the population. Right? So naturally things are going to stop. But even though this intuitive thing is in our head, I would say that maybe when we were writing down some of these models, for instance, logistic growth, it wasn't obvious where the resources were, right? Or what to do if the resource amounting increases, or the rate at which resources are being supplied increases, and so on and so forth. I just resources were implicit, not explicit, in these kinds of models, right? And so one thing that you might think about, and this is one kind of modeling that we do in ecology, is a class of models where we make the resources kind of explicit, right? And so these kinds of models are what are called consumer resource models. And whenever we're thinking of models, it's always nice to think about where it is that these models are sort of coming from. So let's maybe imagine the simplest case that we might have. So the simplest case yesterday was maybe just one species, right? Just a single species population. What would be the simplest case for a consumer resource model? One species and one resource, right? For instance, so I'm going to make some symbols throughout my lecture, but maybe I'll make some wiggles if I'm talking about species, right? So maybe I'm talking about species, and maybe for now I'll call it species one, because eventually we're going to have more, eating one resource, right? So this resource is going to be this triangle. Right? And in principle, this the species will only grow if it consumes this resource, right? And so when we want to write down a model, we want to track something about these species and resources, right? So what might we want to track? We might want to track the biomass of this species, for instance, right? Or the abundance of this species. So kind of the same kind of variables that we were talking about yesterday. I believe we were using x's, so I'll try and continue to use the same. So maybe we're talking about x, and we want to write down some dynamics for how this x changes with time. So we'll be interested in writing down at least one equation of this type. Do we have to write anything else? Right, so this resource also, presumably the amount of this resource also changes over time, right? So we measure that in some unit, your favorite unit, maybe it's the mass of the resource, maybe it's some generic density of the resource. But in principle, there's going to be some resource amount, which we're going to measure, that we can call maybe R, right? And so we're also going to, and this resource amount will change with time. If it didn't change with time, then of course, species could in principle be growing forever, right? So we're also going to care about the resource amount changing with time, right? And so we want to write down maybe the simplest possible dynamics that we can think of that explains the relationship between these species and these resources, right? So I mean, in general, in any kind of these dynamics, you'll want to write down this as some function, f, this as some function g, and Could anyone say something about what this function f should maybe depend on and what this function g should maybe depend on? Should this function f only depend on x? X and r. Why? Can someone say why x and r? Right. So there's an explicit dependence on the resources of what? What's the thing that comes up here? Like, what does this f mean? It's a function, but what does the function mean in English, right? What is it representing biologically? It's the growth rate, right? It's the growth rate of the population of species one, right? So this growth rate presumably depends on how much resource is there. You know, that's the whole thing that we're playing around with, right? And and what about this function g? What does this function g represent? It's the depletion rate of the resources, right? I mean, so in principle, this resource is being depleted by the species, but is there anything else that's happening? Yeah, maybe there's some supply of resources, right? Maybe this resource is coming from somewhere outside, and it's coming in at some rate. Maybe in some cases, and in fact, this is the case that we're going to work with today. This resource is not coming from outside. We'll kind of think of this resource as itself a biological species, right? So maybe it's like, you know, you can think about this as being a rabbit or a population of rabbits, and then this species that maybe consumes it is going to be something that eats the rabbit, right? So you can think of your favorite rabbit eaters. But yeah, you know, does anyone have their favorite rabbit eater that they want to put on the board? Foxes, sure. I'm not entirely sure if foxes eat rabbits, but I'm completely fine to put it over here, right? So so in principle, these are rabbits, right? And so rabbits are these biotic populations, so they'll grow, right? And so in principle, this G will incorporate the fact both of the resources being renewed at some rate. Either they get renewed because they're being supplied from outside or because they're growing on their own. You know, the rabbits are eating the grasses, in fact. So in principle, there's a grass somewhere that is implicit in what we're thinking about, right? And so this G would this depend on just R or just X? This would also in general depend on both X and R, right? Right, so you know, the most general kind of consumer resource model for one species and one resource might look something like this. But of course, if we want to do any kind of analysis, we need to think about exactly what to say for these F's and G's. So let's take maybe the simplest possible example that might make sense. So for the species, you know, we spent a lot of time discussing this yesterday. You know, we know that, for instance, Spallanzani did things. So we know that, you know, if a species is not there, it can't spontaneously be sort of generated. So there's always this nice X sitting outside. So if X is 0, dx dt is always 0. And then there's something here that I put in parentheses, right? And the something here is what we're going to fill in. But can someone quickly tell me what this something here represents? There's a particular name that we've been giving it all through yesterday, right? It's the per capita growth rate, right? So in principle, what we have to do here is to think about a simple version of what the per capita growth rate of the species will look like as a function of the resources that are available. And so one simple choice that you might make is to say that maybe the species is eating this resource with some propensity or some rate that you know, maybe you can call C. You know, C has to do with consumption. So maybe the simplest form that you can write down here is something that looks like this, right? So it's a linear function, the simplest function in terms of R that you can imagine. And let's just check and see if it does the sort of basic things that we wanted to do, see if it passes some simple sanity checks, right? So what are some sanity checks that we should do here to see if this functional form that I wrote here makes sense? So we already talked about the fact that when X equals 0, the growth rate should be 0. The population shouldn't grow, right? Is that happening? And yeah, I forgot to say this, but maybe during the class, you know, it would be nice if everyone could participate. So I'm going to ask lots of yes/no questions. So, you know, thumbs up yes, thumbs down, no. So I ask anything, just feel free to take your thumb and make it go up or down. This also helps with if your hands have pins and needles. So yeah, okay, so it passes this simple check. Any other simple checks that anyone can think about?
Would be that if the resource is not there,
yeah,
then the population of the species will decrease.
Perfect. Very nice. So if there's no resource, that is when R is 0, the population should be dying exponentially, right? Is that something that happens in this model? Yeah, right. So in fact, we know exactly now what M is. M is the per capita death rate of this particular species in the absence of any resource, right? So that's the per capita death rate, or sometimes people might think of it as the maintenance rate. There's some resources that you have, they grow at, you're getting resources at some flux. If you get them at a certain flux that beats your maintenance cost, you grow. If not, then you die, right? So this is a per capita death rate in the absence of any resource. Okay, any other checks? What about now when you have a little bit of resource, just a tiny bit more than 0? Do you grow or do you die? Yeah, it depends a little bit on what these parameters, right? But generally, when R is 0, you'll die for sure. When you increase R a little bit, you probably will still continue dying, but maybe at a smaller and smaller rate, right? And then eventually, if you have enough resources, then this term can become positive, right? And in that case, you can grow, right? So this is also a thing that makes sense to us, right? If there's enough resources, then you should grow. If there's not enough resources, then you should die. Of course, if there are 0 resources, you should die for sure, right? So maybe this is one perhaps simple, maybe the simplest kind of functional form for this F that we could write down for one species and one resource. Is everyone happy with this? Any nonsensical things that this function does that anyone would like to point out? Blows up. Okay, where does it blow up? Okay, yeah, that's a very good point. So when R is, of course, large enough so that this growth rate is positive, it seems like you have a positive growth rate and you should keep growing forever, right? But is that something that will happen? Right? Yeah. So we have these dynamics for R that we haven't written yet, but our intuition, certainly the one that we started off with, was that the dynamics of R should be such that when the species is consuming this resource, the resource should get depleted, right? And so that brings us very nicely into thinking about what this G should look like, right? So in principle, this G should definitely have some component that tells you about the impact of other consumers consuming this resource, right? So here we have just one consumer, and so perhaps the simplest thing that I can write down would be something like this. And let's just again see if this thing makes sense. So I'll just for now I'll write down some H here. This will be something to do with the supply of the resources that we'll come to in a second. But this is the term that has to do with depletion, right? And so again, whenever we're writing down one of these models, we should just check to see if it makes sense. So, okay, why did I write it down like this? Why didn't I just write down maybe something simpler like C times R? Yeah, so if I had just C times R, then of course, if I have resources that's being depleted, but these resources could get depleted even if I have no consumer, right? So of course, it makes sense that the more and more you have consumer, the more and more there should be a depletion, the faster and faster. I mean, so simplest thing that I could think of is a linear dependence, at least on the consumer. What about the resource? Why couldn't I have written down C times X? You need R to tell you how much resources remain. Okay, maybe that's one way to think about it. Anything else? Any other simple limit? What happens at R equals 0? When R equals 0, if I had this term for depletion, that means that even when there's no resource, the resource is being depleted, right? So certainly there should be some dependence on R, such that that my depletion should go to 0 when I have no resource, right? And then I just have this same coefficient here that's telling me the rate at which things are being consumed, right? Okay, so that's maybe the simplest form that we can write down for depletion. And then finally, we have to think about supply. And so in this world where we're thinking about this resource as just some rabbit, some other population that's just a single species that's growing, we know how one would go about writing down this H, right? So what's a simple form that one could write down for this H? Yeah, you could write down some growth rate. For instance, you could write down maybe just some R times K or something like that. But this has this problem without for a resource in the absence of any consumer, right? What would the problem be? Yeah, this resource. Oh, so sorry. This resource. These rabbits would keep shooting up to infinity, right? But we know how to fix that part. What do we use?
So doesn't that make sense? Because if you have, you assume that the rabbits are dependent on some grass or something.
Yes.
So in case the consumer is absent and you have infinite presence and you have like enough amount of grass, then it will keep shooting up to.
Right. Yeah.
So essentially, it should depend on the resource that rabbits are.
Right. Yeah, you're absolutely right. There is some implicit assumption that we have about the resource that the resource is eating, right? So the grasses that, for instance, the rabbits are eating, and if your assumption is that grass is, in unlimited supply, then there's no problem in principle with sort of writing this. But if you want to imagine that the grass is maybe not infinitely supplied, then of course there would be a problem, right? So for arbitrary enough reasons, let's stick to the second possibility, and we'll see a little bit in this class why that's a nice choice, outside of the fact that of course the grasses don't blow up or the rabbits don't blow up in the absence of any consumer. So I mean, we discussed this a little bit. Yesterday, the simplest thing to do is just have logistic growth, right? Some version of something that looks like logistic growth, right? So what would now this do in the absence of any consumer? Yeah, so you have your resource. If there's of course no resource, if you start off at R equals 0, you stay at R equals 0 forever. If you have just even a little bit of resource, we know that R equals 0 is this unstable fixed point. So you go and get attracted to R equals what? K, right? And at R equals K, you have a fixed point and it's stable, right? So in the absence of any consumers, these rabbits, these resources are at some fixed population size K. Okay, and so perhaps that's the simplest model of this kind that you might write that you might write down. Okay, and then what do we do whenever we encounter a model of this kind? Well, first we can ask ourselves if these kinds of dynamics are linear or non-linear, right? So are these dynamics linear? Is that's a thumbs up, or non-linear? That's a thumbs down. Yeah, they're non-linear. And why is that? Okay, so in the R, there's a power of R squared. That's true. What about in the dynamics for X? No, I don't have to substitute the value of R, right? Is there anything that's happening here that will tell me that the dynamics are linear or non-linear? There's an Rx term, right? So I have two sort of variables, R and X, and I'm multiplying them, just like Abby was telling us yesterday. If you have any term of that kind, these dynamics are non-linear, right? So okay, they're sort of non-linear dynamics. So maybe we can't solve them fully, but we can certainly say something about some aspect of these dynamics, right? So what is it that we can talk about? We can talk about fixed points, right? So, okay, all right, no, so we'll all do a little exercise where you'll think by yourselves first how many fixed points this system of nonlinear dynamical equations have, and then we'll take a little vote, right? So you'll just use your hands. If you think there's one fixed point, you go 1, 2, 3, and then we'll take a vote, and then we'll talk about the answer. Yeah. Okay. So is the question clear? We have this system of equations. How many fixed points do we have? Then, of course, we'll talk about which they are. Yeah.
Choice of constants.
Mm-hmm.
One is that there should be, perhaps in general, unless you're working with the pre-scaled variables and so on, a parameter for the growth rate of rabbits.
Oh yeah, no, you're absolutely right. Yeah, so in principle, there should be something out here and so on and so forth. I'm just trying to work with something which has the smallest number of parameters that I can write down. But yeah, you're absolutely right. They like truly, I should be writing down something here that's very similar to logistic growth that we wrote down yesterday, which had two parameters, right? This R and this K.
Yes.
For now, just because I want to capture qualitatively things, I'm not going to worry about the growth rate sitting
So
outside.
that's simply a rescaling of time, if you like.
Right. Yeah.
So that's all right.
Yeah.
The other thing is that you're also assuming that the units, in some sense, of resource and the actual species X are the same, and that all the resource gets converted into into biomass of species. Yeah. Because the two constants C are the same.
Absolutely. Yes. So thanks for bringing that up. So this is absolutely true, and this is chosen for simplification. But actually, you brought out an important point, which is that these C's being the same is actually a very special choice in these consumer resource models. And actually, in more generalized versions of these models, you'll call this a set of C's and this a set of some other thing that you can call E's. And you can ask what happens as these things become more and more different from each other. And actually very interesting dynamics happen that we can talk about offline. Yeah. Okay, any other questions? Are we good to take a vote on how many fixed points? So remember, whenever we're talking about fixed points, we're going to think about now both things, right? R and X. This is a 2D system. So any fixed point will constitute knowing both what the X star is, so to speak, and the R star is. Okay, so let's take a vote. How many fixed points? Ready? 3, 2, 1. Okay, let's not say anything. Let's just use our hands. Hands don't talk, right? And then you'll get an opportunity to talk. This is very nice that you want to say things. Okay, so I would say there are a mixture of 2s, 4s, and 3s. Okay, I'm going to give you a little bit of an opportunity. Maybe take 30 seconds, turn around to your neighbor or your partner, and just try and convince them or talk to them about what you think the answer is. Presumably, those who found 4 can help find some of their neighbors 2 extra or 1 extra fixed point that they have. Okay, I see some of the talking is dying down a little bit. Maybe we'll take another vote now and see if the composition of answers has changed. All right, let's take a vote again. How many fixed points do we think that this system has? Ready? 3, 2, 1. Okay, the composition has certainly changed. Okay, the distribution has certainly changed. I would say there are more 2s now. Still a bunch of 4s. Okay, great. Maybe the people who are in support of 4 can tell us which 4, and then of course, maybe we'll see all of them. Maybe we'll find that some of them are not really fixed points or something of this kind, right? Okay, anyone? Okay, let's just start listing some of them, right? So maybe can someone tell me one fixed point? 0, 0. 0, 0 is a nice one to start with. So there's 0, 0. What else? 0, k. Okay. Does everyone agree that 0, k is a fixed point? So that corresponds to a situation where there's no consumer, only this resource, logistic growth. Anything else? Yeah, so people certainly have more than two. Okay, so this is sort of maybe the first one that we're talking about in which both things are present, right? So what is it? K minus R by C. Okay, but R, you mean R star? Okay, K minus R star by C. And what? And M by C. Okay, and so if R star is M by C, then you get what? K over C minus M over C squared. Is that right? Yeah. Does everyone agree with this? I actually haven't done the algebra. I'm actually pretty bad at algebra. M over C seems correct. And so it's either that X is 0 or X is not 0, in which case R star is M over C. You put that in here and okay, everyone happy with that? Okay, and then there's a fourth fixed point. Where's the fourth fixed point? So maybe there's someone thinking about a fixed point where a consumer is present and maybe not the resource. Okay, biologically, certainly that's not possible, but we already talked about the fact that if there's no resource, the consumer dies exponentially, right? So yeah, where's the some people had a fourth fixed point, so maybe we don't have one now. Okay, yeah. So I would say there are three fixed points, right? So we're happy with all of them. There's one, of course, one so-called trivial fixed point, which there are no resources and no species, no consumers. Of course, it's a fixed point, but it's not a very interesting one. Then, of course, this second fixed point is a fixed point that we talked about in yesterday's classes on logistic growth, right? This is the case in which you have just one species going on its own. There's nothing kind of consuming it, so everything's fine. And then this third one is the first interesting one that we find that comes up in this kind of model, right? So this is the case where you have some steady state resource concentration and some steady state consumer or species concentration or abundance or density or what have you, right? Okay, great. Whenever we find answers like these, it's always nice to see if they make sense or not make sense. So let's just check and see what the consequences of this kind of solution are, right? There's also, of course, every time we encounter fixed points, there's always a question that we should be asking right after it, which is what? Are they stable or not? And I'll leave it to you to check which of these fixed points are stable and which of these fixed points are not stable. That's an exercise that I'll leave for you. But okay, and so for a little bit of time, I want to spend time sort of chatting about this fixed point. So does someone have any observations about this fixed point and what it looks like and maybe something interesting about it? So it depends on all these three parameters that we wrote down, right? It depends on K, it depends on M, and it depends on C. Does someone notice something that happens as maybe C increases or C decreases or something like that? So let's maybe focus on talking about the steady state resource concentration. This is something that's often called, for good reason, R star, right? And this will actually relate to something that we'll call the R star rule very soon. And you'll hear about this a little bit more in the coming classes. Okay. So we learned that this R star, the steady state resource concentration, has is some ratio M over C, right? So let's just make sure and see if this implies the things that we hope it to imply. So C was what? C is sort of the propensity or this coefficient that's telling us how quickly the species eats this resource, right? So if a species is presumably really good at eating a resource and capturing it, would C be large or would C be small? Large, right? So, okay, and so what happens to R star as C increases? It decreases, right? And so what does that imply? Is that something that makes sense to us? the resource is certainly not dying, but the steady state abundance of this resource is shrinking as the species is getting better and better at consuming it, right? And this kind of makes sense. There's a rate at which this resource is being supplied by growing, right? If from the perspective of the consumer, and then this consumer is eating it, so the more and more it depletes it, the lower and lower its steady state concentration should be, right? And this has actually a very interesting consequence as soon as you start thinking about two species, right? So let's just think about this consequence a little bit. Let's say now we have two species that are eating the same resource. There's a species 1 and there's a species 2. They're both eating this resource 1 that we have been talking about all this while, right? So there's only one resource, but I'll still say resource 1. This species eats this resource with some propensity, which I'll now call C1, right? Just to say that it comes from species 1. This one will eat the same resource with something that we'll call C2, right? And so now what change, like if I want to describe that system of two species and one resource, what do I have to change? Do I have to change my equations? Sorry. C equals C1 plus C2, but then what are the dynamics that I'm writing down? Am I still writing down the same number of equations? No. Right? So how? 3, right? And so in principle, I'm still writing down one equation to track R. Now I have some x1, and I also have some x2 that I want to track, right? And so this is going to be some other function. And so in principle, I'm going to have to do something of this kind, right? They're all eating the same resource. And then I also have this new equation that I now have to deal with, right? So now if I want to study this system with these two species consuming one resource, I'll have to think about this system of three equations, right? And so now can you? Yeah, you're right. In principle, there should be an M1 and there should be an M2. For now, for simplicity, let's just imagine a situation where every species has the same sort of death rate in the absence of resource. But you're absolutely right. Okay, so some. Oh yes, absolutely. Thanks for pointing that out. Right. So now we have two consumers of the same resource. So now we have two terms over here. Okay, and so now if you want to say anything about this system, what do you do again? It's still non-linear. So you compute what? You compute the fixed points, right? So, and so yeah, can you say something about the fixed points here? How many fixed points are possible? So in principle now, okay, maybe in the interest of time, you should of course try this out, but let's just think about it a little bit together, right? So when we were talking about fixed points for this system, where there was one species and one resource, we had these intuitive way of thinking about it, right? There was going to be a trivial fixed point where there was nothing. Then there was going to be one fixed point where there was going to be a resource but no consumer, and there's going to be one fixed point where they're both present, right? So here, presumably, some of those features will stay, right? So of course, there's going to be one trivial fixed point where there's nothing present, right? Then there's going to be, of course, the same fixed point where just the resource is present, but there are no consumers, right? And and now maybe now can someone catch my drift and say something about what are the other qualitative things? I leave the algebra for you to do because I'm sure I'll get it wrong on the board and you're better at algebra than I am. Right, so presumably there's going to be one fixed point where there's some resource concentration, one of the species is maybe gone and the other species is present, this is not trivial at all. So, we'll spend some time thinking about it. Maybe just because of tree, maybe there's also going to be, the other case. Yeah. Right. Great. Right. Yeah. Perfect. So this is exactly what I was coming to. Maybe I'll stick to this for now. Right. So if there's a case where one of the species is out, then we go back to the case where there's one consumer and one resource, right? And at least for R star, we already know what the R star would be, right? What would that be? So let's say if species 2 was surviving, this would be M over C2, right? And if species 1 was surviving, the R star would be M over C1, right? Okay. Let's just spend some time thinking. And presumably, could there be more? Could there be another fixed point? Presumably, one where both of them are present. I'll leave that as an exercise for you to check what happens there. Something funny happens there. Okay. So in principle, there's also one here, but I'm already warning you. The one that I mentioned on top here. Oh, sorry. This is just kind of a table to read out basically what the order of things is going to be. Right. Yeah. But in principle, I don't know. You have to think about whether there's a fixed point in which both species and the resource can be present, and also think about whether it's stable or not. Right. But okay. So I just want to spend a little bit of time talking about this thing over here. Right. So we have two possible cases. One in which there's consumer 1 that's surviving, not consumer 2, one in which the other thing is happening, right? And one clear distinguishing feature of them is the steady state resource concentration, right? So presumably one of these species is going to be arbitrarily better than the other at being able to consume this resource, right? So let's just say maybe for the purposes of what we want to talk about, C1 is greater than C2. Fine, right? Would that tell you something about these single species fixed points? Let's just start by asking, in which of these fixed points would the steady state resource concentration be lower? Is it the one up top? So that would be your thumbs up, or would it be the one below here, which would be a thumbs down? So is the question clear? One of these fixed points is going to have a lower steady state resource concentration. Which of them is lower? Ready? 3, 2, 1. Yeah, this one over here, right? Because it depends on 1 over C. C1 is larger, right? So okay, so great. So we know that, for instance, R star with species 1 present is less than R star with species 2 present, right? And let's ask ourselves, there's this mysterious fixed point over here that we were interested in, right? And that fixed point had to do with both species surviving. So presumably that was one in which they coexisted with each other, right? And coexistence, of course, is one thing that we're often interested in ecology. And so here's one way to think about this coexistence. Say you have this situation where species 1 is present, right? Species 1 is there, this consumer is there at some fixed point. And now you introduce just a little bit of species 2, okay? If these two species were to be able to coexist, what would species 2 have to do in this situation? Maybe we can go back to these dynamics here and just think about it even more simply than do they have to compete, what needs to be larger or smaller. Just I have this x1, right? My x1 is sitting at this x1 star, which has to do with all of this stuff, right? And my R is sort of sitting at M over C1, right? Now I'll just put a little bit of x2, right? Just a little bit. Is there something that dx2 dt will have to be that if species 2 were eventually able to survive and coexist with species 1? Right. Yeah. So I mean, maybe the simplest thing would be the species will have to grow, right? If you put a little bit of it, it'll have to grow, And for it to grow, this should be positive, right? And of course, this x2 will always be positive because it's a population size. So the way that it could ever be negative is if this thing was negative, right? So all that we need to do is to check whether C2R minus M in this situation is positive or negative, right? And so we need to know what R is. We know what that is. So we have x2 dot is x2 times C2 times R, which is R1 star, right? And we know what R1 star is. That's M over C1 minus M. And we know that we want this thing to be positive, right? And this of course implies the thing that people were just saying, which is what? C2 will have to be larger than C1, but that contradicts something that we have already, right? So this tells us something about these, whether or not these species will be able to coexist with each other, right? What does it say? Substitute the R over where? Yeah. No. So remember, the situation that we are imagining is that we have species 1 and resource 1. They've reached a fixed point. Now we're introducing a little bit of species 2. Right? So just when you introduce this little bit of species 2, the resource concentration just then is the resource concentration that's steady state dictated by species 1. Right? You can also play a similar game with this other fixed point over here, right? Where there is just species 2, and you're asking whether a little bit of species 1 is able to grow or not, right? And can you guess what you will find just by doing this little exercise? Right, you'll find that this species is able to what is called invade this population, right? So it'll be able to grow and invade in this population, and actually eventually what you'll find is that the species 1 will outcompete the species 2, right? So actually coexistence in this case is just, or at least stable coexistence in this case is just not possible.
Coexistence in general, it's not possible. One way to look at it is like to say I have to solve these two equations, right?
Yes.
Imagine that x1 and x2 are different from 0, then the thing in parentheses has to be 0. But how can I take two different lines?
Exactly, right? So the only case in which it could ever be possible is in this sort of degenerate case where C1 and C2 are the same thing, but then in that case they're the exact same species, so what are you even talking about, right? So so actually mathematically, as you'll see, if C1 and C2 are in general different, then there's no coexistence, right? Yes. Yes, I did, but maybe I'll mention it again. So initially I had assumed arbitrarily that C1 is greater than C2. I was allowed to do this, but I just was asking whether or not in a situation where there's just species 1, a little bit of species 2 is able to invade or not.
So that was necessary to get to the state of having all these species.
That was necessary for at least species 1 and species 2 to be able to coexist with each other. No, C1 greater than C2 is what we assumed, right? And what we found was that for coexistence, or not for coexistence, for species 2 to be able to start growing in a population where there's a species 1, we would need the opposite to be true.
Why was that?
Oh, I mean, one of them needed to be larger, so I just chose one thing. So what we were caring about is this. Yeah. Maybe I'll spell it out a little bit more clearly. So what we learn here, and this is really what the R star rule is the following. For in this kind of really simple model where there's just one resource, when every species is sort of growing by itself, there'll be a steady state resource concentration that it's able to get. Maybe this is in general maybe going to be true for other F's and G's that you'll also be able to write down. It's certainly true for this model, right? And this steady state resource concentration tells you a little bit about how competitive this species is, right? So the more competitive a species, the lower this steady state resource concentration R star. And so one consequence of a species having a lower R star and thus being more competitive is that it prevents other less competitive species from being able to grow when they are present. right? So in some sense, if C1 is greater than C2, then species 2 cannot invade in a population where species 1 is already present. But it can do the other way around. It can invade a population where only species 2 is present, right? So in some sense, and this is often something that people will talk about in ecology, there is a so-called R star rule. And this is a rule attributed to Tilman. And it's also called Tilman's R star rule, which is that the more competitive species can drive down the concentration of resources in general, and maybe any specific resource in particular, down to a lower and lower possible value. So the more competitive the species is, the lower this R star would be. And the reason that works out is sort of exactly this, that the lower and lower R star is, the sort of easier and like the harder and harder it is for other species to grow in the presence of this population. Okay, is that clear? So yeah, sorry if this C1, C2 thing was a bit confusing. That's really the aim of what we were talking about. Yeah.
Is it biologically natural for us to arrive at an unstable fixed point when we look at the temporal dynamics?
The question is whether or not it's biologically plausible that you will actually reach an unstable fixed point. I would say no, right? Yeah, usually if you find an unstable fixed point in a system where, in some biological system that you're modeling, you will not imagine the system arrives at that state. Yes?
So one of the kind of factors that somewhat condition is predicated on is that the ends are the same.
Yes.
If the mortality rate of the species differs, is it possible to have coexistence?
You're absolutely right. Thanks for bringing that up. So you're right that here we assume that the M's for these species are both the same, right? In general, there could be some M1 and M2. And so the first thing that we'll see here, and this you can verify, is that actually the thing that matters for this exact reason is not C1 and C2 being larger or smaller. It's actually R star being larger or smaller, which is a combination of M and C, right? So indeed, if your C1 and C2 were different, these two species could still coexist. But in this other degenerate case, where M1 and M2 were poised just perfectly so that their ratio M1 over C1 matched exactly the ratio M2 over C2. Any other questions about this? Why it's R and not C is sort of, the idea for it is exactly this invasibility condition that we were talking about. So what you do is you figure out the fixed points where each species survive on their own, try to invade a little bit of the other species, and try to derive the condition for what that would require, right? And generally, this thing always looks like CR minus M. So for this to be positive, R star, some R star would have to be greater than some M over C, right? And M over C is exactly the R star of that species on its own. So, it's really a battle of the R stars. Yeah, so this is not clear, try it out yourself, but also come to me after class and we can have a little bit of discussion. Okay, so this is sort of relatively clear. I want to spend maybe the last 35 minutes talking a little bit about now what do you do if you want coexistence for two species, and however far we get in it is fine. The idea here is to just first start thinking about it, right? So we saw this scenario where there are we saw the scenario where with one species, one resource, everything seems fine. We saw this scenario with two species and one resource, and everything was very much not fine if you wanted these species to coexist. So presumably you can now do one more thing and hope for the best and the ability of these two species to coexist. Two resources maybe, right? So maybe you think about another resource 2. And then now you think about the dynamics of this whole system with how many equations? 4, right? So now we have to think about an R1 and an R2 instead, in addition to an X1 and an X2, right? So let's spend a little bit of time talking about this and how we start to analyze systems of. Oh, sorry.
So is it
Yeah.
is the case then in this case?
Yeah.
Of those 4 fixed points, only one is true.
Yes. Yeah. True. Yeah. Because this one, if you start to add a little bit of the other species, will also sort of go away. So there's one and only one fixed point that's going to be stable. That's going to be the one that corresponds to the more competitive species being present and excluding the other species. So actually good that you mentioned it. There's another thing that we often talk about in ecology, which is called the competitive exclusion principle. This is sort of one perhaps simplest way to sort of state it, which is that if you have this situation where at least there's just one resource, then the more competitive species, which is, and the competitiveness as we saw is determined by its R star, excludes the other, right? And then we will see that basically if you add more and more species, you're able to you get more and more species to be able to coexist with each other. Okay, so now we're going to, maybe I won't erase this bit over here. Now we're going to talk a little bit about this model with 2 species and two resources. And so now, I mean, you can presumably still think about how the dynamics would look like, but let's just write them down together. You'll still have these M's for the maintenance rates of these species. You'll still have these K's that will tell you a little bit about these resources growing logistically, right? But you'll also have to think a little bit about these C's, right? So how many numbers will we now have to think about when we think about the C's? 4, right? So, and there's going to be, in principle, species 1 is going to be able to eat both resources. So you're going to want to think about the ability, C corresponding to species 1 eating resource 1, and C corresponding to species 1 eating resource 2. Right? So this is some convention that I'm choosing, where the species comes first and the resource comes later. And again, for species 2, there's going to be a propensity with which species 2 eats resource 1 and species 2 eats resource 2. Right? So in principle, we can organize this information in the form of a matrix, right? Where our species come on the rows and our resources come on the columns. And so in this case, we have resources 1 and 2, species 1 and 2. And so we have this C11, C12, C21, and C22, right? And so now maybe you can already imagine what happens when you have more species and more resources, right? In principle, this matrix grows. The more and more species you have, the more and more rows you'll grow in this matrix. The more and more resources you have, the more and more columns you'll get. But this is the first time you have to think about this object here, which is called different names, but it's often also called the consumption matrix. And now let's just think about how we want to change our dynamics over here to account for all of the changes that we've made in this model. Let me just try and make space for all 4 equations to come in one go. So I have my R1, right? And there's R1. I'm going to erase this part now here. It's going to grow logistically with some supply rate K1. And what do I do here? So of course, I talk about R1 now. I still talk about X1 and X2, but these C's now changed, right? So now I have to account for the fact that I have a C matrix. So all I need to do is think about resource 1 being eaten. Resource 1, like the resources go on the columns, right? So I have C11 and C21, right? And so similarly, you can write down the equation for R2 dot, right? That's R2 times K2 minus R2 minus C12 R2 X1. This is species 1 eating resource 2. And this is C22 R2 X2, right? Does this make sense? You just have more and more. Yeah. So did you understand what C was in the sort of previous models? You understood what C1 was and C2 was. So in all of the cases thus far, we were just talking about species eating a single resource, right? So we never had to talk about which resource we were talking about because there was only one, right? Now we have two resources. So whenever we're talking about consumption preferences or consumption rates, we also have to specify which resource we're talking about, right? So I mean, this C11 and this C21 are what we used to call C1 and C2. Right now, we're just putting a 1 at the end to remind ourselves that this is for resource 1. Right now, in C1, 2, and C2, 2 would in another scenario only be C1 and C2, but we're just putting a 2 at the end to remind ourselves that this is for resource 2. Yes?
Earlier, when you had rescaled the growth rate of R1, you had said that it could be absorbed in the time. So now there are two
species and they have two different growth rates.
Yeah, so you're absolutely right. So in principle, now we should be thinking really about these rates being, coming with some extra parameter over here. For the purposes of simplicity and not carrying around too many factors, I'm not going to include. I'm going to assume they're all 1 here. But yes, in general, you would think about that. Okay, now let's just complete this set of equations. We'll want to write one each for x1 and x2. So x1 looks very similar to what we had last time, except now every species is going to be able to eat 2 resources, right? So it gets a resource flux from both these resources. So, maybe for resource 1, I have C11R1. And then what about consuming R2? Should I multiply that with this term? Should I add it with this term? What are the advantages or disadvantages of doing either of those things? So what if I said I did something like this? This means there's something, there's something for like, could you tell me one consequence of writing something down like this? If R1 is 0, but you have plenty of R2, you would still die, right? And so could that be biological? Maybe it could be, right? Maybe let's not think. Yeah, could anyone think of an example where actually that might make sense? Yeah, you could have multiple essential nutrients that you actually need. And if you have those multiple essential nutrients, then of course you can have all the carbon in the world. If you don't have enough nitrogen, for instance, you're still going to die, right? So actually, essential nutrients are something that Sergei Maslov will talk more about in week 2. There's some very interesting dynamics that happen once you have multiple essential nutrients, but I'm not going to talk about them for now. What I'm going to talk about instead is this other concept that we often talk about, which is where we take this kind of sum over here. And can someone think biologically what this might mean? This kind of sum? Yeah, either is fine, both are great, right? So these are what are called substitutable resources often. One resource substitutes for the other. I could have tons of one, none of the other, and I could get the same growth rate that I get with a little bit of both, right? So we are going to work with these kinds of consumer resource models where we have these substitutable resources. And so again, here I might write down something similar. And now just for generality, I have an M1 and M2, which someone brought up before. Okay, so we have four equations. They're still a nonlinear, right? Every time we write down nonlinear equations, we do one thing first, which is what? By now you maybe got the drill. You look at the fixed points, right? And so maybe in this case, actually, maybe you might not have enough fingers on your hands to tell me how many fixed points there are, but can someone say something about how many fixed points you expect in this system? Or how would you start to think about that? Maybe you got some intuition already from thinking about these kinds of models, right? That you didn't even need to do the algebra sometimes to think about, oh, this might be a fixed point, or that might be a fixed point. Yeah, each species, each X could be present or absent, right? Each resource, could it be present or absent? Yes, right. We saw cases in which resources present, resources absent. So that's absolutely fine, right? So how many combinations do we get? Okay, someone says 7, someone says 14. Any other like drops in the hat? Someone said 2 to the power n minus 1. What is n? Yeah, okay. Why? Okay, so you're saying 2 to the power 4 minus 1, which is. Okay, good. Right. So, okay, so let's go through this. So in principle, you know, if you also include the cases where none of them are present, this trivial fixed point, it might seem that there are 2 to the power 4, right? This resource could be present or absent. This resource could be present or absent. This species could be present or absent. This could be present or absent. So there's 2 choices every time, 2 to the 4, which is 16, right? But as someone rightly pointed out, you know, even in this previous case where you had just 1 species and 1 resource, it's not like you had 4 fixed points, right? There was one that was nonsensical, which was the case where resources are absent but consumers are present, right? So you throw out all of those things and you'll end up with some number, right? So you throw out all the ones basically where definitely both resources are not present. Is 1 resource being present okay? Could you have both species surviving on just the 1 resource that's present? No, right? So we just discussed that. So all of those things you'd also have to throw away, right? So you can now compute how many there are. Okay, and in the 20 minutes that we have left, let's just think a little bit about maybe some of the most interesting fixed points here, which is the quest that we originally have, which is why we wrote this model, right? And what is that quest? Let's just have our goal very clear. Yeah, we wanted these species to be able to coexist and hopefully coexist stably, right? So we are really going to be interested in actually the fixed point where everything survives, right? Because we know if just both species survive and just 1 resource survive, that's not going to cut it, right? We already saw that that's not going to do it. So we are going to care about this very special fixed point where all 4 things survive. Okay, and how many such fixed points are there? Let's take a little bit of a vote. Maybe think for 10 seconds of how many fixed points are there where all resources and species are present. The information is all there in the equation, so you should be able to figure it out. All right, let's take a vote for how many numbers you're feeling. If you're feeling 0, then of course go 0, but then 1, 2, 3, 4, 5 up to 10. All right, so how many fixed points where all species and resources are present? Ready? 3, 2, 1. Okay, so the overwhelming majority of the class is saying 1, which I agree with, but we have a question.
Because the relation between C1 and C2 and all those things.
Certainly, all of the relationships would matter, but you know, maybe let's imagine a case where let's imagine the most charitable case that you can think of, or you know, the generic case where you're picking kind of all of them randomly, right? Not these special cases where C1 is exactly C2 or M1 over C1 is exactly something else. Okay, so most of you said 1, which I agree with. Can someone quickly say why there's 1 and why you are sure that there's 1 and only 1 such fixed point? Solve the 3rd and 4th equation. Okay, maybe that's one way of thinking about it. Any other ideas that are perhaps simpler? Some cases in mathematics where you know there's 1 and only 1 solution. You have 4 equations and four variables. That's a nice start. Usually we know that they have 1, 0, or infinitely many solutions for a specific kind of equation, right? what kind of sorry? Degenerate equations. Okay, but let's just think about it more simply. There's like, we all remember this thing about x equations, y unknowns for some kind of equation, right? What's that? Linear equations, right? Are these linear equations? We just agreed when we were starting off that when you put 0 here, which is what we are solving for, and we are solving for the fixed points, these are non-linear, right? This is the first thing that we succumb to. So yeah. So how can we still say there's one? Sorry. Yeah, perfect, right? So we are already getting rid of the case where R1, R2, X1, X2 could be 0. And so they all sort of come out of these equations. We know that they're not 0. So actually the coexistence conditions in terms of R's and the X's are actually linear equations, right? If that's not clear, you can ask me now, or you can think about it a little bit more. But actually, even though these equations are non-linear, the coexistence conditions where you know for sure that the species and resources are all present, those are linear equations. And so those are 4 equations and 4 unknowns, which generally you expect to have a unique solution, right? Okay, so there's this one unique fixed point that in principle we are looking for. We don't know yet whether that fixed point will be feasible or not, right? What did we mean by feasibility yesterday? Yeah, so all resource abundances, all species abundances should be positive. This we still don't know, but in principle, this fixed point should exist, right? And okay, and so you know at this point you can do a little bit of algebra, but in the time we have left, I want to set up just how we start thinking about some of this stuff geometrically. This is also stuff attributed to Tilman. And I will at least be able to set it up in this class. Yes, question.
But the one fixed one is not always given, right? For example, C1, C11, and C12 are greater than C21 and C22.
There's an advantage for species 1, and it will always go to the species 1 invading population.
Yeah, I mean, so we'll talk about all these specific cases. So I'm not like right now. I wasn't talking about, oh, you know, once you give me the C1 seed, you know, once you give me the C matrix, what will happen. I'm just talking specifically about, is it even mathematically possible for us to get something where all species are present, and how many such points would be expected. This is in a case where I let the C's to be whatever value that I want. Okay, and so the way we're going to think about this is called you know, well, it's called many things, but it's attributed to David Tilman. And in principle, you know, I'm just going to call it Tilman's geometric analysis, but you know, different books and papers will talk about them in different ways. So the key idea here is really that we want to be able to draw some sort of portrait or some sort of phase portrait or some sort of flow of the dynamics of these two species and these two resources. And yesterday, when we had just one equation for a single species population, that was very simple, right? What did we do in that case? So we had just some dx dt equals f of x, and we plotted something, right? Right, so we plotted x dot versus x. Right, and so we knew that that was f of x. So we plotted this f of x. We asked where it cuts the x-axis, and then those were our fixed points. And then we could look at stability by looking at the slope locally around this fixed point. Right. This is all well and good when we have just one equation. We have 4. So if we were to draw this phase portrait, that would have an x1 dot, an x2 dot, an R1 dot, an R2 dot, an X1, you know, that's more dimensions than I can draw on a board. So you have to make some choices, right? And in principle, the board only gives us one choice, which is that we can only draw 2 axes. right? So I want to be able to draw things only for 2 axes, and now I have to make a choice. And there's a kind of natural one that Tilman chose that I think makes a lot of sense, and we'll see maybe a little bit of why that's a nice choice. And that is to talk about the space of the resource concentrations or the resource abundances, R1 and R2. So here we are not going to plot R1 dot, R2 dot, or any of the or any of those things. We're only going to look at the R1, R2 plane, and we'll see this is actually quite insightful. Okay, so we've already, agreed that we're going to think of cases where x1 and x2 are both there, right? And so if we have any fixed point where x1 and x2 are present, are they going to look like something on the R1, R2 plane? Maybe let's just talk about x1, right? So we have species 1 eating these 2 resources, R1 and R2. This species is present and it's neither growing nor dying now. So it's in some steady state. So x1 dot has gone to 0. And x1 is not 0. The species is present. Does this look like something in the R1, R2 plane? Okay, someone says it looks like a single point. Why do you think it looks like a single point? Oh, okay, right, good. Yeah, so you're thinking about the situation when R1 and R2 have also gone to a fixed point, right? Okay, that's a nice point. But let's say I'm not thinking about that. Let's say I'm just thinking about what is called a null line in nonlinear dynamics. Are people familiar with what a null line is? Can someone say? Right, yeah, I mean, it doesn't need to be a line. It's some curve generally, along with at least some variable, neither grows nor dies, right? So it's just not changing. So if I were looking for a null line for species 1, what would that null line look like? That would be a straight line in R1, R2 space, right? So I can draw a line that looks a little bit like this, right? And it would have some intercepts over here. What would those intercepts be? Steady state resource concentration. So did we already derive them earlier today? Yeah, so this would be like M1 over C11, right? That's the R1 star for this species, and M2 over C12, that's the R2 star for this species, right? And so that's a line. And the special thing about this line is that x1 dot equals 0 along this line, which is that if the resource. Sorry. The y-axis should be M1, yeah. All of us are going to make these tiny mistakes here and there. Feel free to correct us. Yeah, correct. Okay, and so this is sort of a special line, right? This is this null line. This is a line along which species 1 neither grows nor dies. It has what is called 0 net growth, right? And so for that reason, Tilman called it what is called a ZNGI, which is to say a 0 net growth isocline. Okay, so this is a ZNGI for species 1, and because of this, often this kind of analysis would be called a ZNGI analysis, right? And so the special thing about it is if the resource concentrations at any point in time fall on this line, you know that at least species 1 is neither growing nor dying.
Is there any difference between a ZNGI and a
no, I mean the ZNGI is kind of like a special thing for population dynamics because we're talking about growth. So that's it. This is I'm telling you this term because if you read the literature or if you read some papers here and there, you might encounter this term very often. And so this is for a kind of a special terminology that's used and shows that you're part of the club, so to speak, right? Okay, so let's quickly talk about, okay, this is for species 1. In principle, there's also going to be a ZNGI for species 2, right? And that's also going to look like a line. Yeah, so for species 2, if species 2 is present, there's going to be a null line that's going to come with some other intercepts, right? Maybe before I draw that here and start to confuse all of you, let's just quickly analyze something nice that the ZNGI does, which makes this whole analysis fun, which is, well, can you say something about what this line does to this plane? Or it partitions it into 2, right? And so, if along this line, the species doesn't grow or die at all, presumably on either side of the line, the species does something, right? So is on this side of the ZNGI, is the species growing or is it dying? Ready? 3, 2, 1. Dying, right? And why is that? Because x1 dot is less than 0, right? So over here, x1 dot is less than 0, you get death, right? So for any resource, as soon as resource concentrations are in this zone, this species is always going to die on average, right? And over here, the species is going to grow, right? Because x1 dot is positive, right? And so you can see any fixed point at which this species survives has to do one thing, right? Which is what? Could it be in this region? Could it be in that region? No, right? It has to be on this line, right? So, I mean, right now, everything seems fine. There's lots of points at which this species can survive. All of the fun happens when you start to include now the second species, right? So let me draw maybe one simple example for what happens as soon as you introduce the second species, right? So the second species we agreed is also going to have a ZNGI, which is going to look like a line. And so let's say we have a situation where this is the ZNGI for species 2, right? So this is x2 dot equals 0. The intercepts here are going to be what? Again, m2 over c21 and m2 over c22, right? So it's totally possible for us to choose or have these m's and c's so that this is possible, right? And now can you say something about what you expect when you have both species 1 and species 2 present? Is it possible for them to coexist in this situation? No. Why is that? Right. So there's some sense that we have these ZNGIs must intersect for coexistence. Why is that? Why should they intersect? Right. So we're looking for a fixed point, right? We're looking for a steady state where both species survive. We already agreed that for x1 to survive, that steady state can only fall on this line. Similarly, for x2 to survive, that can only fall on this line. So it's only when these lines intersect can you expect both of these species to coexist, right? So we'll talk about that in a couple of minutes. This situation is then maybe easier, right? This is a situation in which you won't get coexistence. Question is, what will you get instead? Can you say already by looking at this, which species will competitively exclude the other? Okay, so let's take a vote. If you think species 1 will win this battle, 1, 2 will win the battle, 2. Okay, and take maybe 5 seconds to think about it, and then we'll take a vote. So you have all the tools from this lecture. You have this R star rule, everything that we've been building up for a single resource, and everything should just generalize and apply to this case. Okay, so which species will win if this is what the ZNGIs look like? Ready? 3, 2, 1. Okay, a sizable number of you are saying 2. So I agree with you. Can someone quickly say why 2? R star. Okay, so what is it about R star? I mean, first of all, now there are 2 R's, right? So for each species, there are 2 R stars, right? So what do you have in this scenario? Like, why do you say that species 2 is just better? both its R stars are less than that of species 1, right? That means this species is in some sense more competitive on both resources, right? And so this species will survive. Is there another way to think about things? So let's just think about this invasion business that we were doing earlier in the class, right? Imagine that we have species 2, which survives. And so we know if it survives and it's present at a fixed point, the resource concentrations must fall on this line, right? So let's say it's that point, right? And let's say we introduce a little bit of species 1 to this situation. Can we say for sure whether it will grow or die? It will die, right? And why is that? Because you're on this sort of lower part of this of its ZNGI. Right? So this species will not be able to invade. Whereas the other case where you have species 1 present, if you put species 2 in, it's able to grow in this situation, so it will be able to invade. Right? So this is a simple way that you can see that species 2 will be able to competitively exclude species 1. So whenever you have these simple ZNGIs where one is always sort of below the other, you know that species is just plain better at everything, right? And that's now you didn't have to do any math, you didn't have to do any algebra, nothing. You just had to think about these intercepts, plot them, and you know straight away who is going to win this battle, right? So now the only thing that we agreed that makes coexistence possible is the case where now these ZNGIs can actually intersect. Right, so I'm not going to keep writing these intercepts around. But this is presumably one situation, right? So let's say this is x1 dot equals 0. This line is x2 dot equals 0. And we just want to think a little bit about coexistence, what it might look like, because we're not going to be able to go into all the nitty-gritties of stability and so on and so forth. Okay, so if these species are able to coexist, we already know what R1 star and R2 star are, right? What's that going to be? It's going to be this point, right? Because this is the only point at which both species neither grow nor die. So we already know what R1 star and R2 star are, right? And what we don't know is what are the abundances of both these species? Will this coexistence be stable or not? And these are things that, if we spend more time thinking about these models, and you can certainly go try it yourself, you can work it out. But I just want to now talk about, you can work this out, and what you'll see is that yes, in this case, stable coexistence is certainly possible. But I just want to end with a little bit us thinking about, in terms of this R star that we were talking about, maybe why might it be intuitive that both these species could coexist with each other on both of these resources, or what condition had to be true, right? So can someone say a little bit about that? Yeah. Yeah.
R1 star of the first species should be greater than the R1 star of the
right. Yeah, absolutely. Right. So there's some sense which we built up during the class, that there's a sense of competitiveness of a species. That competitiveness can be maybe encapsulated in this R star. Right? So there are 4 R stars that we have to deal with. And so whenever a species is better at consuming a resource, there's a sense in which it draws down the concentration of this resource lower than the other species, right? So the simplest way for both these species to coexist would be if one species had a lower R star than the other, and the other species had the lower R star on the other, one of the resources, one species is better, the other species, the other resource, the other species is better. And actually you'll see that's exactly what's happening here, right? So on resource R2, species 2 is better. It has a lower R star. And on the other resource, species 1 is better because it has a lower R star, right? And so, this is sort of why this idea of R star is sort of nice and generalizes in principle to even more species and more resources. So this is certainly a situation in which 2 species can survive on 2 resources. And like I said, there's more things to think about what this means and what you can say about it, but we are out of time. I think this was a nice discussion that we all had about thinking about these kinds of models. You'll see more of these during the rest of the school. But with that, this is the end of this class.